Hello, I'm Norman Wahlberger. This is the fourth lecture in a series on linear algebra, and today we're going to talk about area and volume, which are central aspects to the subject. There are also topics that overlap with calculus, because determination of areas of various figures is a central problem for calculus and one of the motivating problems of that subject. The approach that we're going to take to area here in linear algebra is quite different to the one in calculus. And today's lecture is not only going to talk about areas and its extension to volumes, but also we're going to talk about interesting two-dimensional versions of vectors called bivectors. These were things invented by an obscure German school teacher called Hermann Grassmann, and are becoming increasingly important in mathematical physics and in mathematics. So let's start with the traditional thinking about areas. You all probably know that the area of a triangle is given by base times height divided by 2. The area of a rectangle is given by the length times the width. The area of a parallelogram is very similar. It's the length times the vertical height. And then there are many other formulas. For example, the area of a circle of radius r is pi r squared. Now all these familiar formulas involve the notion of distance, either distance of the base or height or a radius. In linear algebra, we're going to look at another type of formula which does not involve distance, because we're setting up our affine geometry in a way that's independent of distance. Let's see how that goes. So in affine geometry, we like to start off with a system of parallel lines in two different directions defining an affine grid plane. This is sort of our basic reference frame that we're going to use to try to measure things in this plane. Now suppose that we have two other vectors, say that vector A and that vector B, determining this parallelogram, which I've labeled O, A, B, C. Let's denote by delta of AB the area of that parallelogram as measured by the person who's created this sequence of little parallelograms. So one of these little parallelograms is going to have area 1. So 2 of them is going to have area 2, 4 of them is going to have area 4, and so on. And we'd like to know, what is the area of this parallelogram? Well, this parallelogram is not nicely arranged with respect to the lines of our grid plane. So it's not just a question of direct counting. But it's not too hard to see that an indirect counting process allows us to find the area. And there are two ways of doing that, one which I call external and the other internal. So the external approach, we look at this bounding rectangle right here. That one we can find the area of because it's 1, 2, 3, 4, 5, 6 in this direction and 4 in this direction, so it's got to have the area of 6 times 4. And then we're going to subtract from that these little triangles, the 4 of them on the corners here. Now how are we going to measure the area of a triangle? Well, this one here is half of this parallelogram here, which has 4 and 1 as its dimensions. So the area of the triangle should be 4 times 1 divided by 2. Similarly, this little triangle has dimensions 3 and 2, so its area is 3 times 2 over 2. This little triangle here is much like this one. It's also 4 times 1 over 2, and this one on this side is much like this one. It's 3 times 2 over 2. Now another way of thinking about that is to think, well, we could just take this little triangle and this little one here opposite and put them together by translating. Then we would get a little parallelogram of sides 4 and 1. So another way of making this computation is to say, well, let's start with the parallelogram of sides 6 and 4, and then subtract one parallelogram of sides 4 and 1, representing the sum of these two triangles. And let's also subtract another parallelogram size 3 by 2, representing the sum of these two triangles. Either way, we get 24 minus 4 minus 6, that's 14. Now the other way of thinking about this is to think about it internally. So we're not going to go outside our parallelogram. We're just going to stick inside it, and we're going to make these little cuts here denoted by the red lines. That divides the parallelogram that we're interested in into an internal parallelogram of sides 2 and 2, and again 4 little triangles. And those little 4 triangles have areas 4 times 1 over 2, and 3 times 2 over 2, and 4 times 1 over 2, and 3 times 2 over 2. And so again, get exactly the same story, but now we're adding 2 times 2 plus these 4 triangles. And again, we could restate that in terms of a lot of little rectangles or parallelograms by combining these 2 triangles to make one parallelogram of sides 4 and 1. And we can combine this triangle with this one to get a parallelogram of sides 3 and 2. And when we make this computation, we get 4 plus 6, that's also 14. So in both ways, we get the same answer. That's good. We now have an internal and an external way of calculating very explicitly, essentially by cutting and pasting, the area of an arbitrary parallelogram in the plane. Now let's look at the question, well, what's the general formula? This is a special case. What is the general formula that incorporates not just this example, but all examples? So now let's have a look at the same problem, but somewhat more generally. So we'll start off with a general vector A and a general vector B. And let's agree that the coordinates of the vector A are little a and little b, and the coordinates of vector B are little c and little d. I hope you don't get confused by my use of AB here and AB here. Alright, so what is the area of this parallelogram formed by these 2 vectors? Well, we're going to make the same kind of computation that we did in the previous case, but now we're working with these letters instead of particular numbers. If this is A and this is B, and this is the vector CD, this is a negative in this case, so the number of segments here is actually minus C. So we can label the various parts of this diagram A, B, D, minus C, A, B, D, and minus C. And then the same calculation that we did with the external approach from the last time is the big rectangle has dimension A minus C over here, because that's A and that's minus C, to altogether A minus C, and B plus D in that direction. So that's the big area. And then we subtract the areas of the rectangle formed by those 2 triangles, dimensions A and B, and the rectangle formed by these 2 triangles. And their sides are D and minus C, so we have to subtract minus CD, because the C is actually negative in this picture. Okay, when you expand this out, what do you get? You get A times B, but that cancels with that A times B. You get A times D, that stays. You get minus CB, which stays. And you get minus CD, which cancels with this plus CD. So altogether, we get the very important formula AD minus BC, which is an expression that you've already seen before in our first lecture, and that's no coincidence. So to summarize, the area of this parallelogram, whose sides are given by the vectors AB and CD, is equal to AD minus BC. Now let's have a look at a different configuration showing that the analysis that we've done here is not exactly general. That if the parallelogram is shaped differently, has a different physical configuration, then the argument may have to be modified. So here's a different kind of parallelogram where the vector A is now in this direction, the vector B is in this direction, and the parallelogram does not fit inside a box exactly in the same way this one did. But nevertheless, you can go through what we just did, the same idea, and it turns out that you get the same answer. So rather quickly, how does that work? Well, in this case here, there's A, there's B, that's the vector AB. The vector B is the vector CD, so that's C and that's D. D up there, or also D from here to here. So the area of this big thing is A plus C, there, times B plus D. There's B, there's D. And then we have to subtract what? What do we have to subtract? Well, there's these two little boxes here. There's this little box here and here that appear that haven't appeared before. And that's B and C, so their combined area is 2BC. And then left over we have four triangles. And this one here is AB. So together with the opposite one, it gives us a rectangle of size AB that we have to subtract. And this one here, together with its opposite over here, has CD as its dimensions, and we have to subtract that as well. So when we work out this particular case, we get something a little bit different. Now we get AB, which cancels with that one, AD, which stays, BC, and we subtract 2BC, so we get minus BC, and we get CD, which subtracts from there, so we still get AD minus BC, the same formula in this case. And it's an excellent exercise for you to work out some different looking parallelograms and find that the same formula always works. This is some kind of universal formula, and there's some justification for thinking that this is actually perhaps the most important formula in mathematics. It's an area formula, and it extends to volume formulas, as we'll see later on. And this family of formulas describing areas and volumes and so on in linear algebra is, in my view, the most important function in all of mathematics. We'll talk a lot more about that, but now let's have a look at what it is exactly that we are really doing when we're making this kind of computation. So the kinds of arguments that I've been talking about so far in terms of taking a parallelogram and dissecting it into little pieces and moving them around and counting, it's very attractive, very elementary, but it's not sufficiently algebraic and general for us to easily imagine how to extend it to higher dimensions. So we need a little bit more conceptual understanding of what it actually is that we're doing when we're measuring area. And a good way of focusing our attention on the right issue is to ask this question: what exactly are we taking the area of? Well, you could say, well, a parallelogram. Yes, but what exactly is a parallelogram when we draw that? Is it a set of points? Is it an equation? Is it given by its four corners? Well, there's various possible answers to this, but a very interesting answer is one that was discovered by a German school teacher in the 1840s. His name was Hermann Grassmann, and he introduced the idea of a bivector. At the time, his ideas were almost completely ignored, but in the last 100 years, they've become increasingly important in not just mathematics, but also mathematical physics, and also into the intersection of linear algebra and calculus. So he introduced this idea of a bivector, which is what? Well, a vector is a one-dimensional quantity. It's a directed line segment. It has a direction, and it has a one-dimensional extent. Grassmann said, let's think about a two-dimensional version of a vector, and let's call it a bivector. So what is a bivector? Well, it's some kind of two-dimensional version of a vector which has extent in two different directions. So it's given by a vector A in one direction and another vector B in a different direction, and this little parallelogram that we draw here represents this bivector. So the vector A is a directed line segment. That's what we've already been talking about. And now we introduce this idea and this notation of A wedge B to be a directed plane segment. That's a bivector. Now I must make an important remark about our notation. The notation that we're using, this wedge, is somewhat non-standard. In fact, it's very non-standard. It's used by people in robotics, but it's not very often used by mathematicians. Mathematicians usually use an upside down V. There are a lot of good reasons, however, for using this join wedge, this up wedge, and that's what we're going to use because it really represents like the union of A and B. It's something that's bigger than A and B. It's what we get when we put A and B together. So we're going to say A wedge B, or if we want to be specific, A up wedge B. Okay, so what kind of an object is this? Where does this come about? Does it have any physical significance? In fact, it has very important physical significances that we're going to talk about now. Bivectors arise naturally in physics in a number of different but connected ways. A very simple example of a bivector is what happens when you try to undo a bolt using a wrench. Okay. So imagine there is a bolt, and we put our wrench on it, and then we have to undo it. So how do we do that? Well, of course, we have to apply a force. And if that bolt is on very tight, we're going to have to apply a very big force. And for that, two things are required. First of all, we have to have a bit of strength. But secondly, we have to have a wrench which is long enough. If our wrench is not long enough, then even if we're rather strong, we will not be able to get the right leverage to undo that bolt. The other thing that's rather important is that we have to know in what direction to twist this bolt. Most bolts untwist in this direction, the sort of positive orientation, but there are some bolts that are opposite, and you have to know that, otherwise you're tightening instead of loosening. So some experience with this kind of situation shows that the torque, or the amount of twisting power that you are applying, is dependent both on the length of the wrench, which we're going to call R, and the force that you apply to the wrench, and the direction of F with respect to R. So we're going to call the torque by little tau, and here's a little diagram illustrating the wrench by a vector R, the force by a vector F, and the torque turns out to be essentially described by the bivector that's determined by these two vectors. In other words, here are some empirical facts that you can determine by just experimenting with wrenches. That for a fixed R, the torque is proportional to the force. So if that length is fixed and we double the force, then the amount of twisting is doubled. The second fact is that for a fixed F, the torque is proportional to R. So if we have a fixed amount of force that we're able to apply, and we double the radius, then the amount of torque that we're applying is twice as much. So that means that even someone who's not as strong can still undo a tight bolt if they have a wrench which is long enough. So the torque is proportional both to the force and to this radius R. Another fact is that adding a multiple of R to F leaves the torque unchanged. That's a very important idea, so let's make sure we understand that. So here's R and here's F. In this case, F is being applied perpendicularly to the wrench, which is the obvious thing to do. But suppose that you decide to change the force by adding a multiple of R to it. So there's the direction R, so we add that multiple. We have a new force now acting in this direction. This force, F prime, is longer than F. Okay, because we've added that perpendicular direction to it, it's longer. But now we're pushing harder at an angle which is not perpendicular to our wrench. And experience shows that in that case, the amount of twisting power that we're applying is the same. The torque has not changed. The geometrical interpretation of that is that it's really the area formed by R and F which is crucial, which is determining the torque. If we move F to F prime by adding R, what we're doing is we're shifting from this rectangle to this parallelogram, but the vertical height is still the same, so the area is unchanged. So it's really the area of this thing which is proportional to the torque. Similarly, if we add a multiple of F to R, then tau is also unchanged. In terms of this area, these two principles here suggest that if we double the radius and we half the force, then the amount of torque will be the same. So that this picture here and this picture here, assuming this R is twice that and this F is half of that, these two pictures represent the same amount of torque or twisting power. In terms of Grassmann's bivectors, we say that this bivector is the same as this bivector. Finally, somewhat obvious fact is that if r is parallel to f, then tau equals 0. In other words, if you're silly enough to apply your force in the direction of the wrench, then nothing happens. So if there's our wrench and we apply a force like this, or we apply a pulling force, well, it's not going to do anything to untwist our bolt. And that corresponds in terms of the area picture to the situation where you have a parallelogram formed by two parallel vectors. Well, such a parallelogram is degenerate. It has no area, and so the corresponding torque is 0. So all of this is encaptured by this idea that the torque is physically really the same as a bivector r wedge f. This is our first example of a bivector occurring in physics, where a physical quantity depends on two vectors in a way that's directly proportional to the area of the parallelogram formed by them, and which is unchanged if we scale one of them and unscale the other by the same amount. The next occurrence of bivectors in physics is with angular momentum. And to introduce angular momentum, let's first talk about linear momentum. So if you have a particle traveling with velocity v in a certain direction, and its mass happens to be m, then its momentum is m times v. This is the amount of momentum that it has, the amount of carrying on that it wants to do. This momentum p is a vector because it's a multiple of the vector v. And to give you an idea of how momentum is used in physics, suppose you have two particles, one coming in this direction, one coming in this direction. And suppose that the momentum of this first particle is given by this vector p1, and this momentum here is p2. Now, as I've drawn it, this p2 vector is bigger than p1. Now, this doesn't mean that the second particle is going faster. It could be that the second particle is actually going slower, but its mass is much bigger than the first particle. That would mean that its actual momentum vector is bigger than the momentum vector of p1. So this momentum vector is representing the product of the velocity times the mass. And one of the important laws is the conservation of momentum, saying that if you have two particles and they collide like this and then they scatter off, their new momentums p1 prime and p2 prime have the property that their sum is the same as the sum of the original two momentums. This is vector addition. Okay? So this momentum plus this momentum, that's a vector, is equal to this momentum plus this momentum, even though they may be going off in different directions. And another important use of momentum is to rewrite Newton's law, which was F equals ma. Remember, the a was the acceleration, which is the rate of change of the velocity with respect to time. So if we have m times that rate of change of velocity with respect to time, we could put that m inside, and we see that's just the rate of change of the momentum with respect to time. So that's actually a simpler form of Newton's law. The force is the rate of change of the momentum with respect to time. Okay, that's a linear momentum, and now let's talk about angular momentum, which is what you get when you have a particle that's rotating around a fixed center. For example, it might be attached by a string, or it might be attached via some indirect force, like a gravitational or an electromagnetic force. So I'll write that fixed particle S, where you can think of a sun, and you could think of this as being some kind of comet or something that's going past the sun, or that's perhaps a little toy on a string that's orbiting around the sun. Now suppose that this little particle has a linear momentum p, exactly in the sense that we've been talking about. So there's the vector p, and that particle's position is described by a vector r emanating from the sun to where it is. So we have these two vectors, r and p. Now this particle has a certain angular momentum around the sun. And this is a kind of momentum that's measured around, or rotational kind of variant to this linear momentum. And this is also, usually denoted L, it's also represented in physics by a bivector, r wedge p. In other words, it's really a quantity that depends on the area of this parallelogram rather than on the individual vectors r and p. So if you double r and halved p, then the angular momentum would be the same. This also has a direction. In this case, it might be like this. And if you interchange r and p, then the orientation is interchanged and the angular momentum is negative of what it's used to be. And there's a corresponding law exactly corresponding to this that expresses the torque in terms of the rate of change of this angular momentum with respect to time, which is exactly proportional to this force here being the rate of change of the linear momentum with respect to time. So there's a kind of a parallel story here between the linear and the angular case, and the angular momentum is naturally a bivector. Another area of physics where bivectors naturally play a role is electromagnetism. So if you have a magnet, like north and south, has magnetic lines of force, something like this, then that magnetic field generated by a magnet can interact with electric fields in a rather interesting way that was laid out by Maxwell in the 19th century. So for example, if you have a single electron, there it is there, moving in a magnetic field, so if we just take part of this thing that's a magnetic field, then this electron empirically often has a helical trajectory. And that's the result of a certain bivector occurring, because this electron has a certain velocity. Let's call the velocity v. And if the b represents the magnetic force, then it's an empirical law that that electron will feel a certain force. And that force is at right angles to both the magnetic field and its velocity. And it's given by this equation here, so which, well, we don't need to know exactly what this means, but roughly it's a vector which is perpendicular to these two, whose length is proportional to the area of the parallelogram formed by B and V. So again, this is a bivector situation. It's not B itself or V itself which determines the size of the force, but the combination of B and V through the area of the parallelogram formed by them. So again, if you double B but half V, or the other way around, then the force is unchanged. So the actual law here has a minus sign because the electron is a negative charge, and Q is the charge. So if you have more than one electron there, then the force will be bigger. Okay. Now, physicists these days realize that it's really useful to think rather in terms of the cross product, which we'll talk about later also, but as a replacement of that, to think in terms of this bivector instead. And that becomes especially important when we look at the relativistic aspect of Maxwell's equations. In that case, the bivector formulation simplifies Maxwell's equations considerably. So those are three very natural and important uses of this idea of a bivector in physics. Now let's see that it also simplifies our understanding of areas, because it allows us to think about areas purely algebraically. That's what we want to do. This is linear algebra. We want to apply algebra to the geometry. So when we introduce a bivector, we can just work with the expressions and the various laws that this expression is going to satisfy, which are motivated by the physical examples that we've already been talking about. So our definition that in the plane, a simple bivector is an expression of the form A wedge B, where A and B are vectors, with certain conventions. And our conventions are the following: that if we multiply A by some number lambda, then that's the same as multiplying B by that same number lambda. And so we'll write either of these in the form lambda times the bivector A wedge B. The second rule that we require is that if we add a multiple of B to A, then the bivector doesn't change. And similarly, if we add a multiple of A to B, then the bivector also doesn't change. And if we take the bivector formed by A and itself, that's a parallelogram with two vectors in the same direction, then we should get 0. Well, it's what kind of 0? Well, it's the 0 bivector. So let me tentatively introduce this little vector notation, suggesting that it's not a vector, it's not a number, but it's a bivector, and it's the 0 bivector. All right, so that's what a bivector is, and now what can we do with them? Well, we can perform operations on them much like we perform operations on vectors. What do we do with vectors? We can scale or multiply them, and we can add two of them. Well, that's the same kind of thing that we're allowed to do with bivectors. So if we have a bivector A wedge B, then we can form 3 times A wedge B. If we have a bivector C wedge B, we can form, say, minus C wedge B. But we can do more elaborate things. We can combine different ones. So we could take 5 times this bivector plus 2 times this bivector minus this bivector. We can form linear combinations of bivectors, of simple bivectors, and we'll call such a thing still a bivector. And now there are 2 more laws that we have to add onto the ones we already have. These are the distributive laws. We are going to agree that if we have A plus B wedge C, then that's the same as A wedge C plus B wedge C. And the other way around, if we have A wedge B plus C, then that's the same as A wedge B plus A wedge C. So our convention is that if we have an expression like this, the wedges are combined first and then we add later. Geometrically, this has an analog for linear momentum and the other examples too. If we have some particle here and there's a linear momentum to the particle here and then another linear momentum to the particle there, you might have 2 particles, for example, that are glued together, one there and one with 2 different linear momentums. Then the combined linear momentum that both those particles have is given by this sum vector here. So this is B plus C, this red vector. And we're saying that the angular momentum due to the first and to the second added up gives us the angular momentum due to the sum. Now here's an important consequence of these laws, which is an important result. It tells us that when we interchange the 2 vectors in a bivector, then the bivector changes sign. So it's not commutative, it's almost commutative, but there's a minus sign that appears. And this is a consequence of this distributive law and the law that we had earlier. The law that we had earlier is that if you take any vector and wedge it with itself, you get the 0 vector. So if we have 2 vectors A and B and we take A plus B and we wedge it with A plus B, then we must get 0. But we can also expand this kind of product using the distributive laws. There's going to be 4 separate wedge products. There's A wedge A plus A wedge B plus B wedge A plus B wedge B. And there the 4 are there. But now we see that there's an A wedge A. We've agreed that that's 0. And this B wedge B is also 0. So there are really only 2 terms in this, namely the A wedge B and the B wedge A. And together those 2 terms are supposed to add up to 0. And if 2 things add up to 0, then one is the negative of the other. So telling us that A wedge B is minus B wedge A. That's an important property of the bivector product. And we'll see later on, we're going to talk more about this in later things, but you can see that this wedge is acting a little bit like a multiplication, and that's sort of the way you should think about it. It's a way of multiplying 2 vectors to give you a bivector. This next result shows that if we're working in the plane, the theory of bivectors is in fact very simple, because in the plane every bivector is a multiple of one basic bivector, say E1, E2. What are E1 and E2? Well, they're any 2 vectors that you're using to start your grid plane framework. All what they have to be is in different directions. I'm going to give you 2 proofs of this, one geometrical with pictures and one completely algebraic. So here's a geometrical proof. Let's say there's the vector E1 and there's the vector E2. And I'm now going to look at an arbitrary bivector, call it A wedge B. So there's a random vector A, there's a random vector B, and this oriented parallelogram represents the bivector A wedge B. And I want to show you that this bivector A wedge B is actually a multiple of the bivector E1 wedge E2. We do it in a couple of steps. First of all, we change this by replacing B with a new vector obtained by adding a multiple of A. And which multiple of A? Well, we're going to add a multiple of A just enough to get us down to the E1 direction. So there was the old B, and now I'm going to move in this direction, which is in the A direction, to get this vector B2. Okay? So there was our old bivector, and here is our new bivector, obtained by replacing B with B plus a multiple of A. So that's now A wedge B2. But one of our rules for bivectors is that does not change the bivector, because we're adding a multiple of A to B. So this bivector represents the same as this bivector. All right, now we can do something similar to this one. What we're going to do is we're going to shift it over in this direction. So there's what we're starting with. And now instead of A, we're going to have A2. So how do we get that? We move in this direction of B2. We move in the direction of B2 to replace A2 with, rather to replace A with A2. Okay. So our old bivector was this one, and our new bivector is this one. But now we see that this bivector here is some multiple of E1 wedge some multiple of E2. We don't know what the multiples are, but there are some multiples. And then by our rules for multiples, the alpha and the beta both come out, and we get alpha beta times E1 wedge E2. Showing that this bivector is actually a multiple of the bivector formed by E1 and E2. Here's a completely algebraic proof of the same thing. No pictures. So we assume that our vector A is some multiple of E1 plus some multiple of E2. And our vector B is some multiple of E1 plus some multiple of E2. And I'm using A and B and C and D for these coefficients, just like we have been before. And now we're going to make an important computation. We're going to compute the product in the bivector sense of these two vectors. There's AE1 plus BE2 wedge CE1 plus DE2. And we're only allowed to use the laws that we've agreed on. Well, the distributive law says the first term is this times this. Well, we could write that as A times C times E1 wedge E1. The next term is this times this. So that's AD times E1 wedge E2. Next term, BE2 wedge CE1. That's BC times E2 wedge E1. We're not allowed to change the orders of these wedges. And finally, BD times E2 wedge E2. Now when we look at these four expressions, we see that two of them are 0. The E1 wedge E1 is 0. The E2 wedge E2 is 0. But moreover, the E2 wedge E1 is negative E1 wedge E2. We change the orientation, we change the sign of the bivector. So this becomes AD minus BC times E1 wedge E2. This is a very important formula because now we see that this AD minus BC term, which is the same formula that we found for the area of a parallelogram formed by these two vectors, has an interpretation purely in terms of bivectors. It's simply the multiple of this basic bivector represented by the bivector A wedge B. It's a very important idea. Okay? The idea that we can get at the area of the parallelogram formed by A wedge B simply by making this computation with this bivector formulation. And it's just a question of this bivector being a multiple of this bivector, and that's the coefficient, that's the multiple. That multiple is the area. So let's have a look at that result in an explicit example. Here is a grid plane formed by two vectors E1, E2, and this time I've decided to put the E1 up in that direction and E2 in that direction. We can do it whichever way we want. We have a lot of little parallelograms formed by our two basis vectors. And now here come two random vectors A and B, and they happen to be 2E1 plus 5E2, so that vector there is 2E1 plus 5E2, and the vector B, this one here, is 3E1 plus E2. And they form this parallelogram right here, and that parallelogram represents the bivector A wedge B. Now algebraically, we can work out what that bivector is by taking this expression and wedging it with this expression. So we get 2e1, e2. Remember the e1 wedges disappear, the e2 wedges disappear. So we get 2e1, e2 plus 5 times 3, that's 15 e2 wedge e1. And we have 2 minus 15 is minus 13 e1 wedge e2. And in terms of the coefficients, that's 2 times 1 minus 5 times 3. That's that AD minus BC combination that we've seen many times already. So that's now the signed area of this parallelogram AB with respect to E1 wedge E2. We see that this number AD minus BC can be negative. So it may not be exactly the area notion that you're used to. If you're used to area always being positive, you have to change your mind here. You have to be a little bit more flexible. In linear algebra, areas can be negative. And it's better perhaps to think in terms of signed area. This is really the crucial quantity. So the signed area of A wedge B with respect to our basic E1 wedge E2 bivector, that's the one that we're starting with for our entire framework, that's going to be then this multiple. Delta A wedge B is minus 13. We also might just say that that's the signed area of A comma B. The signed area determined by these two vectors A and B with respect to E1, E2. And if we want to make the dependence explicit, make sure that everybody knows we're talking about E1, E2 because there may be other vectors in the situation, we'll put E1, E2 down here at the base of this delta function. So this is saying that the signed area of AB with respect to E1, E2 is minus 13. And this is telling us that area is a relative concept. In affine geometry, there's no absolute area. It depends on how you measure, how you set up a measuring system. Once you set up a measuring system, then you can talk about areas, but it's really areas relative to your measuring system determined by two starting vectors. So here we have two more examples. We have a basic framework represented by E1, E2. They're going this direction this time. There's our basic parallelogram formed by our basic basis vectors. And now we have this parallelogram formed by a vector F1 and F2. And F1 is 4E1 plus E2, and F2 is minus 2E1 plus 3E2. And from this, we can compute that the bivector F1 wedge F2 is 4 times 3 minus 1 times minus 2, that's 14 E1 wedge E2. Telling us that the area of this parallelogram is 14 times this area. Now here's another little parallelogram formed by this vector G1 and this vector G2. Again, with respect to E1 and E2, G1 is E1 plus 3E2, and G2 is minus 5E1 minus E2. Again, our same formula says that when we wedge these two together, we're going to get 1 times minus 1 minus 3 times minus 5. So that's minus 1 plus 15, that's minus 14 E1 wedge E2. And so we see that this bivector F1 wedge F2 is minus the bivector G1 wedge G2, because both of them are plus or minus 14 E1 wedge E2. Now this expression is simply a relation between this bivector and this bivector. It's in fact independent of the observer. If someone else came along and measured these two bivectors with a different reference frame, they would still get this relation. They may not say that this is 14 and this is minus 14. They might have some completely different numbers for the area measurements, but they would agree that these two parallelograms have the same area up to sine. So the lesson here, a very important lesson, is it's that the ratio of areas are affine geometry invariants. If we just have a plane without any reference at all, it does not make sense to say, what's the area of some figure? That doesn't make any sense because we don't have any reference frame to pin things down. But if we have two different figures, then we can talk about the ratios of the areas. We can say this is 3 times as much as that. And that's independent of the observer. So it only depends on the affine geometry. So it's ratios of areas which are the invariants in affine geometry. Now let's have a quick look at three-dimensional geometry and how some of these ideas extend to that richer situation. Of course, there's a lot to say about three-dimensional space, and we'll set up the theory a little bit more formally later. But just as an introduction, what we're going to need to discuss three-dimensional space, instead of having 2 basis vectors, E1, E2, we're going to need 3 different basis vectors, and they should be pointing in different directions so that we really get something in three-dimensional space. So here's a little picture, which is now a three-dimensional picture, right? Not just in the plane. You've got one vector E1, one vector E2. You think of that sort of representing a horizontal plane. And then you have some third direction, E3, which we can think of as sort of the up direction. Now in this kind of situation, just with these 3 vectors, there are 3 different kinds of geometrical objects floating around. There are the vectors themselves, E1, E2, E3. And now there are bivectors. And there are different kinds of bivectors. There's E1 wedge E2, which represents that horizontal plane direction. And there's E1 wedge E3, which represents that face of our little box. And over here we have E2 wedge E3, that little parallelogram represents that face of the box. It represents that plane. So we have one-dimensional objects, we have two-dimensional objects, bivectors, but now we also have a three-dimensional object, a trivector. A trivector is what you get when you think of a directed space segment. It's a three-dimensional object, an analog of a parallelogram formed by 3 vectors. We'll write E1, wedge E2, wedge E3. The laws for trivectors are very similar to the laws for bivectors. We agree that if we multiply any one of them by a scalar or a number lambda, then that's the same as multiplying any other of them by the same number. So lambda E1 wedge E2 wedge E3 is the same as E1 wedge lambda E2 wedge E3, which is the same as E1 wedge E2 wedge lambda E3. We require that this thing be linear in any one of the components. So if we have A1 plus A2 wedge B wedge C, then that's the same as this trivector plus this trivector. A1 wedge B wedge C plus A2 wedge B wedge C. And that works not just in the first component, but also in the second component and also in the third component. And we can get at that by this third rule, which tells us what happens when we interchange 2 vectors in a trivector. So if we start with A wedge B wedge C and we interchange, say, the A and B, then we get minus B wedge A wedge C. The trivector changes sign. It also changes sign if we interchange any 2 of them. So if we interchange these 2, we get that with a minus sign. If we interchange these 2, we get that also with a minus sign. So whenever we interchange any 2 of them, we agree that we're going to get a minus sign, just as we did in the bivector case. All right, let's see how we can use trivectors to compute a volume. Here are 3 vectors, A, B, and C, with respect to our 3 basis vectors, E1, E2, E3. So the coefficients A, B, C, D, E, F, G, H, and I. And to record all that efficiently, we could put them in the matrix like that. And what we're interested in is the parallelepiped formed by those 3 vectors. So we can go in this direction, this direction, this direction, A, B, or C, and we can form a box whose sides are parallel to those 3 vectors. And to compute the volume of that box, we compute the trivector formed by taking A, wedge B, wedge C. And it's a purely algebraic computation. There are the 3 vectors, and we're wedging them together. And now we're going to use the algebraic laws for these wedges. The crucial thing is that there are not 27 terms, 3 times 3 times 3 like you might think, because most of those are 0. If we have E1 wedge E1 anywhere in a wedge, then that's automatically 0. So in other words, whenever we have two EI which are the same in a triple, we get 0. So the only ones which are not 0 are the ones involving E1, E2, E3 in some combination. And there are 6 of them. For example, you could take this AE1 followed by this E2 followed by this IE3. That would give you AEI times E1 wedge E2 wedge E3. Or you could take this one here, AE1, times this FE3 times this HE2. When I say times, I'm really meaning wedge. That would give us AFH times E1 wedge E3 wedge E2. And there are altogether 6 combinations. Please check that those are the 6. And then we want to combine them into one expression involving a multiple of E1 wedge E2 wedge E3. To do that, we have to rearrange something like this by swapping the E2 and the E3, and that will introduce a minus sign. So some of these have minus signs and some of them don't. For example, this one will have a minus sign because we need to swap those. This one, what happens there, we need to swap these two, and then we need to swap again. So that BFG will not have a minus sign. 2 minuses make a plus. Here we need to swap those, and then another swap. So CDH will be appearing without a minus sign. And here we need to swap once, twice, 3 times to get into this form, so there'll be a minus sign. This coefficient that appears here is the volume of the parallelepiped, and it's a fundamental formula in mathematics. It's what the 19th century mathematicians called a determinant. And here we see that it's a consequence of thinking about the way trivectors multiply together. These 6 expressions are related to this matrix of coefficients in a very nice way. Each one of these represents a way of choosing one of these from each row and each column. So BFG, for example, BFG, one of them from each row and one of them from each column, and there are 6 ways of doing that. It's in chess notation, the number of ways of putting rooks on that chessboard so that no 2 rooks can take each other. So we're going to have a lot to say about this expression. It's a generalization of that AD minus BC expression that we had before. It represents the volume in 3-dimensional space, and it's crucial for solving our basic problem of linear algebra, which I remind you is how to change from one set of linear variables to another set of linear variables. Next time we're going to have a look at how that works, but let's now give a few exercises. So our first exercise, in the plane, suppose we have 2 random vectors E1, E2, and then we expressed in terms of those vectors, we have vectors A and B, 3E1 minus E2 and 2E1 plus E2. And I want you to find this coefficient, this signed area of AB with respect to E1, E2, both graphically and algebraically. So this number represents the area of the parallelogram formed by these 2 vectors in terms of the reference parallelogram formed by E1 and E2. The second is a similar kind of problem, a little bit more elaborate, because we have now a vector A, a vector B, a vector C, a vector D, and I ask you to compute 3 different invariants. The delta of AB with respect to E1, E2, the delta of CD with respect to E1, E2, and the delta of CD with respect to AB. This is getting you used to the idea that we can change coordinate systems. And there's no God-given coordinate system. It's not always E1, E2. We could be looking at things from the point of view of A and B as being the basic reference frame. So one of the things that we want to do is we want to be able to move fluidly back from one reference frame to another. And our final exercise, a 3-dimensional example. We have basis vectors E1, E2, E3 in 3-dimensional space. And in terms of those basis vectors, we have 4 other vectors. So the vector A is 1, 1, 2. And this notation means that it's 1 times E1 plus 1 times E2 plus 2 times E3. So we have these 4 different vectors, and I want to find 4 different volumes. The volume of A, B, and C, formed by those 3. The volume of the little parallelepiped formed by those 3. Or ABD, ACD, and BCD. Just give you some practice in using the determinantal formula. Next time, we're going to have a look at the basic problem of linear algebra. How to invert a linear change of coordinates. And these notions of area and volume, the AD minus BC formula, and the more complicated one with 6 terms for volume, are going to play a central role. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.